Hello and welcome to this video on the topic of Linux kernel's elemental concepts. This is a research project for British Columbia Institute of Technology Operating Systems course. In this video, I will be giving a brief introduction to Linux. I will then move on to talk about the process scheduler subsystem, the memory management subsystem, and the input-output architecture. So, what is Linux? Depending on the context, Linux can refer to the Linux kernel or the Linux operating system. In the context of this presentation, Linux will refer to the Linux kernel. Linux is widely used. Think of Android or GNU Linux, what it's commonly referred as the Linux operating system, which is also the most widely used operating system for servers. Linux is open source, which means that it is free, and also the source code is open for everybody to see and to contribute to. Linux was created in 1991 by Linus Torvalds. In this slide, we can see a diagram of the Linux architecture. We can see that it is comprised of three main subsystems: the input-output subsystem, which controls the input-output devices such as network, storage, and human interface; memory management subsystem, which controls the RAM; and the process management subsystem, which controls the way that processes are executed in the CPU. To access these subsystems, the Linux kernel provides a system called interface, which is an API that programmers can use to control the hardware. Now, let's explore the process scheduler, which is part of the process management subsystem. About the process scheduler, I have chosen the following topics: process scheduler architecture, generic scheduler, task priorities, scheduling classes, and the complete deferred scheduler. The process scheduler is a two-layer system. It is composed by the generic scheduler, which contains three different scheduler classes, which in turn contain the task entities that are to be executed in the CPU. The generic scheduler serves different purposes. It defines an interface that scheduling classes implement. It contains one instance of each scheduling class. It maintains an abstract run queue containing the tasks allocated in each scheduling class. And it prioritizes non-fair, high-priority scheduling classes. In the next slide, we will talk about scheduling classes. There are three possible scheduler classes: complete deferred scheduling, real-time scheduling, and deadline scheduling. Each class can implement different scheduling policies. The tasks are assigned to scheduling classes depending on their defined scheduling policy. Scheduling policies are the set of rules used to determine when and how to select a new process to run. In addition to policies, tasks also have different priorities. Priorities are used by the scheduling classes to bias the execution order. There are two types of priorities: static priority and dynamic priority. Static priority is used by the real-time scheduling class. It is defined by the user, that is, the programmer. It is not dynamically modified by the scheduler, it is constant. And also, processes with static priority are given higher priority than processes in other classes. Static priority can range from 0 to 99. On the other hand, dynamic priority is employed by all scheduling classes. It is dynamically assigned by the scheduler and is dependent on historic behavior, that is it I/O bound or processor bound, the accumulated runtime, the waiting time, and the nice value of the task. The nice value defines how willingly a task gives up CPU time. It ranges from -20, high priority, to 19, low priority. Now let's talk about the complete deferred scheduling class. The complete deferred scheduling is the default Linux scheduling class since version 2.6.63 from October 2007. It tries to maximize CPU utilization while maintaining interactive performance. that is, having a really fast I/O response. In completely fair scheduling, the tasks run for a dynamic duration of time in the CPU. It also uses a self-balancing binary search tree, also known as a red-black tree, instead of a linked list to implement the run queue. It implements sleeper fairness. Sleeper fairness is that when a task is mostly waiting for I/O, when it finally wakes up, it gets a fair share of the CPU time. Completely fair scheduling handles the shed normal, shed batch, and shed idle policies. The shed normal policy is the default policy for Linux. The shed batch policy handles tasks that are CPU bound. These tasks get allocated a very large portion of the CPU time. However, they do have a lower priority than shed normal tasks. Finally, the shed idle policy is the policy given to the idle process that runs when there are no other runnable processes. Completely fair scheduling also implements group scheduling. Group scheduling is that when a process spawns several threads, the threads share the allocated time to their parent process. This is as opposed to getting a shared slice from the total amount of CPU time. Finally, tasks in completely fair scheduling are always given a static priority of 0. Now, let's delve a little bit deeper into the completely fair scheduling implementation. In this slide, you can see a red-black tree. Each node in the red-black tree represents a runnable task. For each task, we keep track of certain information. That is, the time that it has been waiting to be run, the accumulated runtime, its historical behavior, and its nice value. The historical behavior refers to if it is I/O bound or CPU bound. To determine the order in which the tasks will be executed, the scheduler does an in-order traversal of the tree. Then it selects the node furthest to the left in the tree to run next. Before moving on, there are a few concepts I would like to state. The first is the target latency, which is also known by other names depending on the literature. The target latency is the amount of time during which we would like all the processes to have run on the CPU. Next is the minimum granularity. The minimum granularity is the minimum amount of CPU time that we can allocate to each task. Next is the cycle period, which, although it is not defined in other literature, I think it's important to define in order to make it easier to understand. The cycle period is the actual amount of time that it takes for all the processes to run, as opposed to the target latency. The cycle period can be calculated as the maximum between the target latency or the minimum granularity times the number of runnable tasks. Finally, there is the scheduling frequency. The scheduling frequency is the frequency with which the scheduling algorithm runs. It is usually said to be the same as the cycle period. Now that we have defined some fundamental concepts, we can begin to explore how each block gets allocated a slice of time. In this slide, you can see a representation of a cycle in the colored blocks. The grayed out block labeled number 1 represents the beginning of the next cycle. As you can see, for our example, we have defined a target latency of 30 milliseconds. Now, how do we calculate how much time each block gets allocated? Well, there is a simple formula. We divide the target latency by the number of running tasks. The result will be the amount of time that each block gets to run. Now we can proceed to plug in the values and we get a result of 6 milliseconds. However, what would happen if instead of having 5 tasks we had 10? Then we would plug in our values again and we'll see we would have 3 milliseconds. Now, what happens if 3 milliseconds is just too little and there is not enough time remaining after doing a context switch? What we do in this case is we use the minimum granularity. Let's imagine that we define the minimum granularity to be 5 milliseconds. Then, as the minimum granularity would be larger than what is allocated by our formula based on the target latency, the minimum granularity would override the time slice duration. In this case, the cycle period would actually be 50 milliseconds instead of the target latency, which is 30 milliseconds. What we need to note about the completely fair scheduler is that although it is similar to round robin, it tries to minimize the number of context switching by allocating a proportional amount of time to each task depending on the current situation. It also guarantees that the time slices are going to be considerably larger than context switching. Our final topic related to the completely fair scheduler is what is known as sleeper fairness. As I stated earlier, sleeper fairness is when we let tasks that have been waiting for I/O to go first and get a larger share of the CPU time for this cycle. Let's imagine that task 29 was waiting for I/O for a long time and now it's ready to resume execution. Normally, when a task is being inserted in the run queue, it gets inserted at the end. However, the scheduler recognizes how long the task has been waiting and places it right at the front in the leftmost node of our tree. This allows the task to run next. With this, we complete our exploration into the completely fair scheduler and the process scheduler section. The next subsystem we will be looking at will be the memory management subsystem. From the memory management subsystem, I have chosen the following topics: describing physical memory, memory allocation, including the body allocator and the slab allocator. Let's begin describing physical memory. In this slide you can see a simplified representation of physical memory description in Linux. At first we start with the memory banks, that is, the RAM cards in the computer. For each bank we create a node, and then each node will have a pointer to a linked list of struct page structures, each representing an individual frame in the memory. The node will also contain pointers to different zone structures. The zones are direct memory access for legacy products, normal zone, which is the zone that can be accessed up to addresses of 2 to the power of 32 that Linux can access directly, and finally high memory, for which Linux cannot access directly but needs to use a page table. Each zone also gets an array of structures called free areas, which contain pointers to a linked list of pages, which point to the free pages in memory. We will describe this in more detail in the following slides. Before moving on, let's look at this diagram, which shows us in a simplified way how Linux handles memory allocation. At first, we have our application in the user space, which uses the glibc library to interact with the kernel. Our kernel then sends the request appropriately either to the slab allocator or the zone allocator, and each of these will subsequently interact with the body allocator, which then can interact with the actual physical layer and allocate memory. As we're following a bottom-up approach, the next step after describing the physical memory is talking about the body allocator. The body allocator was invented in 1963 by Harry Markowitz. It is fast and efficient, but it produces internal fragmentation between 28 and 60%. It is used in Linux to manage physical memory. Allocation requests made to the body allocator return a virtual address. It also manages a free area list of size max order, which by default is 10. This free area list is the one that was specified in the physical description of memory slide. To understand the body allocator, we'll begin by talking about the free area list. In the free area list, each item contains a list of page blocks. Each block itself contains a list of physically contiguous struct pages. The size of each block is 2 to the power of order pages, where order is the index where the block is contained within the free area list. Now let's talk about the blocks. Each block contains a list of physically contiguous struct page, size 2 to the power of order, as mentioned before. Contiguous blocks are paired, and pairs are called bodies. Each block can then be divided into half-sized bodies until the block size is 1, and free bodies can be merged into a larger sized block until block size is 2 to the power of max order. To understand what was explained previously, let's look at this diagram. To the left, we have a free area list, which is sized n, which in this case represents our max order. Then we have a list of blocks for each item in the free area list. Each block then contains a list of pages. The amount of pages that each block contains is related to the index in which it is contained in the free area list. As you can see, this block is in the nth element of the free area list, so the block will have 2 to the power of n pages. As mentioned earlier, we can split blocks into half-sized bodies. Let's look at how this works. Suppose that we want a block of size 2 pages. However, in this free area list right now, we don't have any free 2-page block. So what we can do is divide our 4-page block into 2 2-page blocks, and then we can take the 2-page block away for our needs. In the same manner, we can merge smaller blocks into larger blocks. Let's suppose that we needed a 16-page block. We'd begin by merging the 2 2-page blocks into one 4-page block, then merge the 2 4-page blocks into one 8-page block, and subsequently merge the 2 8-page blocks into one 16-page block. As you can see, this will allow us to effectively use memory while avoiding external fragmentation and allocating memory in a very fast manner. While the body allocator is perfectly fine if we want to allocate large chunks of memory, however, what happens if we just want to allocate a tiny minute struct? Then we use the slab allocator. The slab allocator is used by the kernel to allocate objects smaller than a page. It is layered on top of the body allocator, and it provides off-the-shelf initialized objects that are ready to be used. Instead of deallocating, it recycles discarded objects, and it maintains a cache for every commonly used kernel object, such as inode cache, dentry cache, buffer head, VM area, struct, etc. Its purposes are to reduce internal fragmentation that would otherwise be caused by the body system, caching commonly used objects so that the operative system does not have to waste time allocating, initializing, and destroying objects, and to improve hardware cache utilization. Some important slab allocator underlying concepts are the cache, which is a collection of objects of the same type. The cache organizes the objects across a number of slabs, and all of the objects in the cache have been initialized. Then is the slab. The slab is a chunk of memory, usually page-sized, where initialized objects are contained. To aid in memory management optimizations, the state of the slab is tracked. There are 3 different states for slabs: free, none of its objects are being used; partial, some of the objects are being used; or full, all of the objects are being used. In this diagram, we can see a graphical representation of our slab allocator. At the top, we can see a list of caches. It is important to note that this linked list is actually a circular linked list where the tail points to the head. For each cache, we maintain lists of slabs that are full, partial, or free. Then each slab will then contain a list of pages, which then themselves contain a list of objects. It is important to understand that all of the objects within one cache will be of the same type. With this, we conclude our memory management section. In this section, we will be talking about the input-output architecture. Although input-output is a really wide subject, in this presentation we will be focusing on the I/O device management and I/O resources representation and allocation. To better understand the Linux input-output architecture, we'll begin by doing a quick debriefing into computer hardware architecture. As you can see, computer components are connected together by a system of buses. In this diagram, you can see the processor, the cache, and the main memory connected by the system bus. To connect 2 different buses together, we use a bridge, And finally, the data path between any input-output device all the way to the processor is known as an I/O bus. As you can see, there are 4 different I/O buses represented in this diagram. To communicate between the I/O device and the CPU, first the I/O device must register in an I/O port. The CPU can then reference that I/O port with its 16 address pins. And finally, the CPU can send commands, provide or retrieve data using its 8, 16 or 32 data pins. Each pin will represent a bit. Let's look a little bit deeper into how the CPU communicates with the device. To communicate between the CPU and the device, we'll use the following instructions. In and ins for reading from the device, and outs to write to the device. Then, to send the commands and retrieve data, we'll use a standardized structure between all of the devices. You write commands on the control register. You read device status from the status register. You read data from the input register. And you write data into the output register. The same I/O port can be used for all of the above operations. So, what is an I/O port? An I/O port can be a hardware or a main memory address, depending on the context. To us, it will be the latter. Each port is 8 bits, and we can combine 2 ports to form a 16-bit port, given that the first port has an even address. As you can see, in our diagram we have a 16-bit port starting at address 0. However, we could not start a 16-bit port starting at address 1. We can also combine 4 ports into a 32-bit port, given that the first port's address is a multiple of 4. As you can see, we have a 32-bit port starting at address 4. Finally, there are 65,535 8-bit I/O ports. To use I/O ports, we employ resources. More formally, a resource is a device represented as an aggregation of I/O ports. Linux represents these resources as a struct resource. The struct resource keeps track of several data, including the name of the owner of the resource, the address of the first port of the resource, and the address of the last port of the resource, some flags, a pointer to a parent resource, a pointer to a sibling resource, and a pointer to a child resource. As you can see from these variables, the resources are aggregated into a tree. As mentioned in the previous slide, resources are organized as a tree. However, it is not a standard tree. The first thing to note is that the root of the tree will be a struct resource named I/O port resource. The I/O port resource struct will have allocated the full address space for all of the ports. Another thing to note is that the parent will only have the pointer to one of the childs. Every child will also have a pointer to its parent node. And finally, every node will have a pointer to its sibling node, effectively creating a linked list of siblings. Now, you may ask yourself, why a tree? Well, let's consider a scenario where we have a hard disk drive with allocated ports ranging from 0 to 16. As you can see, this hard disk drive is then partitioned into partition C, partition D, and partition E. Partition C will have the ports allocated from 0 to 7, partition D from 8 to 11, and partition E from 12 to 16. From this, we can deduce that port allocation follows a hierarchical model. Now, let's talk about how we can allocate ports in our programs. To allocate ports in our programs, we must include the Linux ioports.h header. And in this header, we'll find the following functions. Request resource, which assigns a given range to an I/O device. Allocate resource, which alternatively finds an available range having a given size for our device. And release resource, which releases the ports allocated to our device. Let's talk about how to actually use ports to communicate with our devices. To do this, we must include the io.h header in the sys folder. This header will define the following functions: out B, out W, and out L. The B, the W, and the L represent byte, word, and long respectively, and each of these writes 1, 2, or 4 consecutive bytes respectively to an I/O port. Out B underscore P, out W underscore P, and out L underscore P. These instructions do the same as the above, however they add a dummy instruction to introduce a pause. Then we have our input functions ins B, ins W, ins L, B, W, and L meaning the same as in the previous instructions, and these read consecutive bytes in groups of 1, 2, or 4 respectively from an I/O port. The length of the sequence, that means the amount of groups, is specified as a parameter of the functions. Finally, we have outs B, outs W, and outs L, which also write sequences of consecutive bytes in groups. With this, we have concluded the final section in our presentation. Now, let's do some recap. In this presentation, you learned to do a basic... Now, let's do some recap. In this presentation, you learned a basic Linux description, the Linux architecture, process scheduling including the generic scheduler and scheduling classes, task priorities, and the completely free scheduler. You also learned how to describe the physical memory allocation including the body allocator and the slab allocator. And finally, you also learned the I/O architecture of Linux, which included the hardware level CPU I/O device communication and resource management. You also learned about the I/O architecture in Linux, which included the hardware level CPU input-output device communication, resource management, resource allocation system calls, I/O device system calls. If you enjoyed the topics that I presented and would like to gain a deeper knowledge, I suggest that you check out the resources in my bibliography. I want to thank you for watching, and I hope that you really enjoyed and learned from my presentation. I am Karel Chanivecky Garcia, and this was a presentation for the British Columbia Institute of Technology's Operating System course.